In this video, we examine the optimization of a heating system using system modeling. Consider a metal rod with different temperatures at each end. Experience shows that heat is transferred along the length of the rod from the hotter region to the cooler one. In general, heat naturally flows from areas of higher temperature to areas of lower temperature due to a temperature difference. This behavior is described by Fourier's law of thermal conductivity, which determines the rate of heat transfer by conduction along a material based on the temperature gradient. Heat also moves from the outer surface of the rod to the surrounding fluid due to the motion of the fluid. This heat transfer process is called convection. According to Newton's law of cooling, the convective heat transfer rate is proportional to the temperature difference between the rod surface and the ambient fluid. Both heat transfer by conduction and convection can be applied to manage and control thermal systems. Any electronic system, such as a computer, generates heat under normal operating conditions. In some cases, the amount of heat produced can reach the system's tolerance threshold. To prevent damage to components due to excessive temperature or overheating, it is essential to remove heat effectively. Electronic surfaces don't have enough natural surface area to remove heat quickly. For this purpose, these systems are often equipped with extended surfaces called fins. These fins extend from the system body into the surrounding fluid to enhance heat transfer. Adding fins provides more contact with the cooling fluid. For this reason, the selection of fins is one of the most important steps in thermal management systems. Fins are classified based on their geometry and application. Common types include simple fins, which have a constant cross-sectional area along their length, and triangular fins, whose cross-sectional area decreases from a maximum at the base, in contact with the wall, to zero at the tip. This figure illustrates a triangular fin with known geometric dimensions, including its length in the direction of fin extension, width, and base thickness. At the point of contact with the wall, the fin is assumed to be at the same temperature as the wall, meaning that the thermal contact resistance between the two surfaces is negligible. Heat is transferred from the wall to the fin by conduction, with a known thermal conductivity, and from the fin to the surrounding fluid by convection through the fin's lateral surfaces. The surrounding fluid is at a known temperature, and the convective heat transfer coefficient between the fin surface and the fluid is given. Heat transfer by radiation is assumed to be negligible. It is further assumed that the fin thickness at the base is very small compared to its length and width, and that temperature variation occurs only in the longitudinal direction. The fin therefore has a cross-sectional area perpendicular to the direction of heat conduction that varies along the length of the fin. Although fins are designed to enhance heat transfer by increasing surface area, they also introduce thermal resistance. This resistance causes a temperature drop along the length of the fin, resulting in a temperature gradient. In an ideal fin, there is no thermal resistance, and the temperature remains uniform throughout the fin, equal to the base temperature. In practice, real fins always exhibit some resistance to heat transfer. The performance of a real fin is therefore evaluated by comparing it to an ideal fin with the same geometry and dimensions. This comparison is expressed using fin efficiency, which is defined as the ratio of the actual heat transfer rate from a real fin to the heat transfer rate from an ideal fin, that is, the maximum possible heat transfer. A triangular fin can be considered as a prism, whose base has a triangular shape with a prescribed area. If the triangular base area of the fin is fixed, the fin volume or weight is fixed. Electronic devices require continuous reductions in size and weight in order to improve overall performance. The goal is not only to enhance heat transfer, but to do so while minimizing system mass and volume. Heat transfer from a fin is commonly expressed per unit width, that is, as the heat transfer rate per meter of fin width. The objective is to determine the fin efficiency that results in maximum heat transfer. By evaluating the fin efficiency, the fin dimensions can be determined, including the optimum fin thickness, which corresponds to the maximum achievable heat transfer. To derive the governing equation, consider a small control volume element of length delta x located between positions x and x plus delta x from the fin base. The surface area of this element varies along the fin length. Heat enters and leaves the control volume by conduction and is simultaneously lost to the surroundings by convection. The general heat balance for the control volume states that the sum of heat input and generation minus the sum of heat output and consumption equals the accumulation. Since the system operates under steady-state conditions, the accumulation is zero. In addition, there is no internal heat generation or chemical reaction in the fin. The energy balance therefore simplifies to the following: the heat entering the control volume by conduction at position x, minus the heat leaving by conduction at position x plus delta x, minus the heat transferred to the surroundings by convection from the lateral surface, must equal zero. Assuming that the fin thickness is negligible compared to its width, the lateral surface area of the control volume element can be approximated as the product of the fin perimeter, approximately twice the fin width, and the element length delta x. The assumption of negligible fin thickness results in a constant fin circumference along the fin. Substituting the conduction and convection heat transfer expressions into the energy balance equation, dividing by delta x, and taking the limit as delta x approaches zero, results in a second-order ordinary differential equation that describes the temperature distribution along the fin length. In deriving this equation, the thermal conductivity of the fin material is assumed to be constant and independent of temperature. To solve the second-order differential equation for the fin temperature distribution, two boundary conditions are required. The first boundary condition is applied at the base of the fin. Since the thermal resistance at the contact between the fin and the wall is assumed to be negligible, the temperature of the fin at the base is equal to the wall temperature. The second boundary condition is applied at the tip of the fin. At the fin tip, the temperature must remain finite. Alternatively, this boundary condition can be expressed by assuming that the heat flux at the fin tip is zero, since the cross-sectional area of the fin approaches zero at that point. By introducing appropriate dimensionless variables, the chain rule for differentiation under a change of variables allows derivatives to be expressed in terms of the new variables. Substituting these dimensionless variables into the differential equation transforms the governing differential equation for the fin temperature distribution into a dimensionless form. This transformation reduces the problem to one that depends on a single dimensionless parameter. This parameter, denoted by phi, represents the ratio between the maximum heat transferred from the fin to the surrounding fluid by convection and the heat conducted from the wall into the fin based on the maximum temperature gradient. In other words, phi provides a measure of the relative importance of convective heat loss compared to conductive heat transport within the fin. This differential equation can be written in standard form together with the given boundary conditions. It belongs to the family of Bessel differential equations, which we first consider in their general form. The general solution of a Bessel differential equation can be expressed as a combination of two Bessel functions. The specific type of Bessel functions is determined by the coefficient c, while the order of the Bessel functions depends on the parameter p, which is derived from the coefficients a, b, and s. If p is neither an integer nor zero, the general solution consists of two Bessel functions of the first kind denoted by j when c greater than 0, and two modified Bessel functions of the first kind denoted by I when c less than 0. If p is an integer or zero, the general solution includes both Bessel functions of the first and second kind, denoted by j and y, respectively, for c greater than 0, and both modified Bessel functions of the first and second kind, denoted by I and k, respectively, for c less than 0. By returning to the original differential equation and comparing it with the standard form of the Bessel differential equation, the coefficients a, b, c, and s can be identified, from which the coefficient p is subsequently calculated. Since p is 0 and the coefficient c is negative, the general solution of the differential equation is a linear combination of two modified Bessel functions of order 0, namely I0 of the first kind and K0 of the second kind. Because the value of the temperature at the tip of the fin is finite, the coefficient multiplying K0 must be 0, as K0 is not defined at the origin, as evident from its graph. Consequently, the solution of the differential equation simplifies. By applying the second boundary condition, namely the temperature at the base of the fin, the coefficient C1 is obtained, and from there the particular solution of the differential equation is determined. Fin efficiency is defined as the ratio of the actual heat transfer rate from the fin to the maximum possible heat transfer rate if the entire fin were maintained at the base temperature. The actual rate of heat transfer is the amount of heat conducted from the base, where the fin is attached to the wall, into the fin. It can also be expressed as the amount of heat removed from the fin surface to the surrounding ambient air through convection. Because the fin is in steady-state conditions, these two quantities are equal. Using dimensionless variables, these relationships can be expressed in terms of a dimensionless temperature and a dimensionless axial coordinate. As noted earlier, the maximum possible heat transfer rate corresponds to that of an ideal fin, one in which the temperature remains uniform throughout the fin and is equal to the base temperature. Fin efficiency can therefore be expressed in two equivalent ways, either by differentiating the fin temperature distribution to determine the heat conducted at the base, or by integrating the temperature profile along the fin surface to obtain the total convective heat loss. Because differentiating the temperature profile is much simpler than integrating it over the fin surface, the first method is typically used to calculate fin efficiency. As can be seen from the characteristic efficiency relation, it is evident that fin efficiency is independent of fin width and depends only on the length and thickness as its geometric parameters. This is why heat transfer from a fin is commonly expressed per unit width, that is, as the heat transfer rate per meter of fin width. This observation leads to an important design question. For a triangular fin modeled as a prism with a triangular base, if the base area, and therefore the fin volume or weight, is fixed, what fin thickness results in the maximum heat transfer? To answer this, we first determine the heat transfer rate from the fin by knowing fin efficiency. The objective is to maximize heat transfer for a fixed base area. By using the definition of the dimensionless parameter phi to express the fin thickness in terms of phi, and substituting this expression into the base area AP, the fin length can be expressed in terms of the base area. Substituting this expression for the fin length into the heat transfer equation then yields an expression for the heat transfer rate. By calculating heat transfer per unit width, we obtain a formula in which the heat transfer rate depends only on phi, while all other geometric and thermal parameters remain constant. Consequently, the heat transfer rate becomes proportional to a function that depends solely on phi. The next step is to find the maximum value of this function. The graph of this function shows a clear maximum point, where the rate of heat transfer from the fin reaches its highest value. To determine this maximum point analytically, the derivative of the function with respect to phi is taken and set equal to 0. With some algebraic manipulation, this results in an equation that must be solved numerically, such as Newton-Raphson method. Solving this equation yields the value of phi that produces the maximum possible heat transfer from the fin surface. Once this optimal value of phi is known, the corresponding fin efficiency can be calculated. As discussed earlier, fins are used to enhance heat transfer by increasing surface area, but the added length also introduces additional thermal resistance. For a triangular fin with a fixed base area, the optimal efficiency is therefore the point at which these competing effects are best balanced. At this optimal condition, although the fin efficiency is only about 60% of the ideal fin, the heat transfer rate is maximized. From this result, the optimal fin dimensions, including both the optimal thickness and length, can be determined for the specified base area and heat transfer conditions. In addition, the maximum heat transfer rate from the fin is obtained under these optimal conditions. This analysis also highlights the importance of fin material selection. Materials with high thermal conductivity significantly improve fin performance. For this reason, copper and aluminum are commonly used. Although copper has a higher thermal conductivity, aluminum is often preferred due to its lower weight and cost. For example, consider an aluminum fin with a base area of 10 square centimeters exposed to cooling air. By substituting the known parameters into the optimization relations, the optimal fin thickness can be determined. In this case, the fin length is found to be much greater than its thickness, confirming that the one-dimensional heat transfer assumption used in the modeling is valid. Thermal management systems, particularly in electronic devices, require continuous reductions in size and weight in order to improve overall performance. The performance of a fin thermal system is determined by a combination of several factors, including the geometric shape and optimal dimensions of the fins, their weight, the pressure drop associated with fluid flow, and the arrangement of the fins relative to the wall and the surrounding components. All of these factors must be considered together in an effective thermal design. From this perspective, a triangular fin represents a better choice than a simple fin when both have the same width and the same volume or weight. The analysis of such fins provides valuable insight into the trade-offs involved in fin design and serves as a useful exercise in understanding fin performance and optimization. I hope to explore more system analysis topics together in the future. Until next time.